On this example, we have a flu vaccine. The flu vaccine has a probability of 80% of preventing an inoculated person from getting the flu. For the 83 people inoculated, find the following probabilities. Now, with binomial distributions, each individual trial needs to have the exact same probability, and knowledge of one shouldn't change the probability of the other. This is generally referred to as independence of these events. And I would say that usually the assumption that these are independent events is probably not going to be accurate. If the flu vaccine fails to prevent one person from getting the flu, it probably will fail to prevent more people from getting the flu, just by virtue of maybe exposure, or maybe because the flu vaccine was not the correct formulation for what was present that year. But we're making the assumption that they're independent by saying that there's just a flat 80% probability rate here. So I feel that that was just necessary to say that we're making a somewhat non-intuitive assumption here. Alright, so we have 83 people that are inoculated. We're trying to find the probability that exactly 10 get the flu. So there are 83 different people that are inoculated. It seems like we're counting the number of people that are getting the flu here, so that's how I'm going to define a success. Alright, the probability, well, there are 83 people inoculated, so n is 83. The probability of a success, the probability of getting the flu, well, this flu vaccine has an 80% probability of preventing them from getting the flu, so the probability of a success here I'm actually going to say is 0.2. You can see this is definitely one of those examples where it's important to define what your success is, because you don't want to start counting the number of people that didn't get the flu, and try comparing that to this 10, because that's going to give you a completely different answer. So the number we're calling a success, somebody getting the flu, n is 83. The probability of preventing, or sorry, the probability of getting a flu is 1 minus the probability of preventing the flu, so that's 0.2 there. And x, in this instance, we're saying the probability that exactly 10 get the flu, x would be 10. I could have just as easily flipped this around and defined a success as not getting the flu, but that would have changed my probability to 0.8 and my x to, 73, because there should be 73 people that did not get the flu. So you can define your success however you'd like to, you just need to kind of stick with it. So to find this probability, we want to use binomial PDF. This is a PDF because I want to find the probability of exactly 10 people getting the flu. And then we'll do NP X. So binomial PDF 83.210, which gives us a probability of 0.0210, round to 4 decimal places. Right? Yeah. Alright. If we want to figure out the probability that no more than 4 get the flu, whenever you see these no more than or no less than, you need to immediately think about, okay, what are all the different possibilities? So I'm going to think about, well, we have n equals 83 still, and p equals 0.2. And we're saying no more than 4 get the flu. So x is less than or equal to 4. 0, 1, 2, 3, 4, 5, 6, ... all the way up to possibly 83 people getting the flu. We're saying that no more than 4 get the flu, so we're trying to figure out this probability right here, probability of those. Now, before, when I was doing anything circled like this, I kind of had to use my complement rule to get essentially the area on the left. But on this one, I don't need to use the complement rule because I can figure out what is the probability of no more than 4. Well, this is exactly the binomial CDF 83.2, and our uppermost limit of this is 4, so we want to figure out the probability that no more than 4 get the flu. This is exactly binomial CDF 83.24. So let's plug that into the calculator. This gives us the probability of 8.004 e negative 5. So that e negative 5 is how this calculator represents scientific notation. So this means 8.004 times 10 to the negative 5th, which means we're going to move the decimal place 5 places to the left. 8004. Starting here, moving it 1, 2, 3, 4, 5 places to the left. So the probability that no more than 4 get the flu is 0.0008. It's quite unlikely that no more than 4 get the flu. The probability that none get the flu, well, let's see. N is 83, P is 0.2, X, again, we're counting our successes as the number of people that get the flu, and so if the probability that none of them get the flu would be X equals 0. This is exactly equal to 0, so I'm not going to use the CDF, I'm going to use the PDF. You can see on this last one, I used the CDF because I'm going over a range of values. On this one, I'm figuring out just the probability of exactly 0 people getting the flu, just this one right here. I would expect this to be quite unlikely, especially since the probability that no more than 4 get the flu is already pretty unlikely. So binomial, it's exactly 0, so it's going to be PDF. My N is 83, there's 83 trials, probability of success of 0.2, and 0 successes here. So binomial PDF 83.20. And we get 9.046 times 10 to the negative 9th. Which is 0.1234567890446. I had to move the decimal place 9 places to the left, which means that I would get 8 trailing 0 or 8 leading zeros the first time I get to the other side of the 9, and then I get 8 more places that I have to move. Obviously, this is really close to 0.